Okay, so next up we have last presentation before lunch, so great responsibility here. We have Juniper, we have Massimo Magnani, and he will be telling us about a rift, rooting in fat trees. And okay. So he will speaking us about rooting in fat trees, which is this protocol that rift in short. Yes, and so we will see the latest about routing in data center environments.
Prova. I've always dreamt of doing that, guys. Hello, everybody. I'm Massimo Magnani from Juniper Networks Italy, in this SDN era, I'm here to talk about routing, which is very uncommon these days, but let's say back to our roots, or to my roots. Basically, we have started in the EATF working group to propose a new protocol that is very effective in topologies like IP fabric. And this protocol is called RIFT, which means routing in fat trees. So, okay. A very quick overview of traditional routing protocol. We know that we have on one side link state protocols that have all their advantages and all their behavior, the distributed computation, all the routers have the same view of the topology, and hence each router can calculate the best path giving the topology itself on one side. On the other side, we have distance or path vector protocols, which is a very different approach as prefixes are advertised hop by hop and metrics are added on each hop, matrix attributes and so on. We all know about this stuff, so I want to go pretty quick here. The point is that after some time in researching how those protocols might work in data center, can work because they are actually implemented in data center today on topologies spine and leaf, which is the most used topology today. We recognize and we acknowledged that neither of them, nor distance path vector protocols, nor link state protocols can take advantages of the very particular topology that spine and leaf is. And from here, we think that we might take advantage of this very particular topology by designing a protocol that can be most effective if used in this topology. As I said, today the topologies that we are seeing are are derived from the close topologies and all the studies that happened in the 50s. Because if you take a look at spine and leaf, topology is like a folded cloth at some extent. And so it's very let's say, understood that this topology provides benefit like I don't remember the word, but either in Italian I don't remember the word. So these topologies are very hierarchical, okay. Hierarchical topologies, okay, I can do that. And also the ratio of oversubscription is quite easy to calculate. And it provides also benefits in terms of economics, because it's not full meshed, but can provide a very, let's say, easy way to manage bandwidth. So, as I said, if we take a look at close topology and we take this beautiful drawing, a 5-stage close topology, and we fold it, we basically obtain the topology that you can see below, which is a typical spinal leaf topology with a different level of devices, let's say. We have superspine, we have spine, we have leaf, or to use Rift terminology, we have the spine level, the aggregation level, and the edge level. So those terminology that you can see there is the terminology that is used by Rift Draft. So we can say spine is like superspine, aggregation is like spine, and edge is like leaf. Where are we now? We know that in several large DC fabrics, there are a lot of implementations that use eBGP with some, let's say, patches or band-aids, or IGP with band-aids as well. And both of these approach can have challenges. For instance, if we think about BGP, then ECMP is not that straightforward. We need that path to support multi-homing and better ECMP, and also to prevent oscillations. We have a limited private AS space. There are some we are seeing also some proprietary extension to protocols such as LLDP trying to address zero-touch provisioning or auto-configuration for fabric. And the reality check is that, in our opinion, what we want in modern IP fabric, which is for sure auto-discovery and SPF, and also miscabling awareness. If I connect a cable in the wrong position, if my protocol can warn me, it is very welcome from a troubleshooting standpoint. And all these principles are diverging from the original principles that carried to BGP standardizations. And so what we are seeing today, eBGP or IGP, ISIS mainly, or BGP over IGP. There are some customers that basically uses the fabric like if the fabric is a backbone. So they run the IGP, and then on top of IGP for the service, they run BGP. But those solutions can't achieve all the requirements that after some time the working group for this protocol could get from customers. And these requirements are briefly listed. The most important ones are listed here. First of all, as I said, auto-discovery, peering auto-discovery, cabling misconfiguration prevention, all this stuff are very important, and it's not easy to have them with the current protocol. But those are built into Rift. Another problem that we may have is that, especially at the leaf level, we are using chipsets that are very good at pushing bandwidth, but are not the best in terms of logical scalability. So the number of informations that, in terms of routing informations, that those devices can store is not very high. So another requirement should be that at the leaf level, the least information, the better, the best. Then, in a current IP fabric, we want to be able to do very large ECMP and to do also non-equal cost load balancing if possible, and we want to have LFA, okay? And BGP is not the best to do that. It can be done with ISIS, but even this requirement is perfectly addressed by Rift. Then we want to do traffic engineering. Why not? And this case is very easy to do that with BGP. It's not easy to do that with ISIS. Then we want to be able to support other upcoming technologies like part computation elements, so routing based on external controller, for instance, or segment routing. And again, very easy to do with ISIS, of course, but even on Rift. Another point that customers ask is the way to be able to transport opaque information very easily. Opaque information, I mean metadata or data that are very important to do auto-configuration. And so Rift implemented the key value pair, let's say, tie, which we will say, which is a tie. Tie is like, let's say, an LSA, okay? And so it will be possible in the future, using Rift, to communicate information that are not routing information, but can be also configuration information or provisioning information through this key-value pair. Another interesting feature is the automatic disaggregation on failures. What does it mean? It means that on Rift, if I lose some path because of failure, and I can land with a topology that can lead to black hole or suboptimal routing because of failures, then Rift automatically, and we will see this in a couple of slides, automatically will disaggregate the prefixes in order to restore connectivity or optimal routing. And another paramount, in my opinion, a very important, maybe the most important one, is the blast radius. The blast radius is the radius of propagation in case of fault. Okay, if I have a fault and all my routers are in the same level or in the same area, then I have to recalculate everywhere because the fault will be reflected to all the router in the area, for instance. So if my data center is made of a single level, a SIS level, then the blast radius is basically to all the data center devices. With Rift, we will see that in case of failure, the blast radius is 1 hop. So it's minimal, okay? And then, of course, the fastest possible conversion of failures. We will see that Rift is at the same time a distance vector and also IGP like OSPF. Okay, sorry. And so it can react very fast to failures. And the simplest initial implementation means that it must be very easy to implement. In this case, we know that BGP is implemented in a lot of implementations. ISIS as well, let's say. Not very easy to implement, but we have implementation. Rift is easy to implement if we look at the tools that we can use to implement it. But of course, it has to be implemented carefully because it shares some similarities with the link state protocols. So the implementation is not that simple, but of course it's perfectly doable, especially if one has already an experience with ISIS. So let's jump to concept, topology constraints, and so on. This is the basics of Rift. If we take a look at, this is the reference topology that is written on the draft. Okay, so we are reasoning on this topology, but all the principles are, of course, completely the same also in other spine and leaf topologies. And of course, we are not limited to 3 levels. We can have also more levels above. The first characteristic is that Rift is behaving like a link state protocol in the north direction. So Rift has a very important concept. Each node is represented differently depending on the direction it shares information. So we have a north direction and we have a south direction. And based on these directions, the information exchange happens in a different way. So in the north direction, Rift is behaving like a link state protocol. It means that Rift LSAs, let's say, that are named ties, topology information elements, are distributed and flooded very similar to a link state protocol. But Rift is behaving like a distance vector protocol in the south, because at the end of the day, one of the advantages that we can leverage from such kind of topology is that we can also advertise at the far out in the south direction in order to achieve ECMP and optimal routing. I'm referring, of course, in case where everything is working properly. I mean, all the links are up, everything is up. So, but Rift has another interesting, let's say, characteristic. Rift will take advantage of this very hierarchical topology by reflecting from one level to the level below in order to be able for the same device, the devices on the same level, to have the visibility of the peers of the same level where they have no east-west link. Okay, so Rift in draft 03, which is the actual one, Rift added the support to east-west links because they were not supported in Rift until draft 03. They were added. But even though we don't use east-west link, we have this reflection feature that allows, in the case of this slide, allows the right red box to know about the left red box, even though there is no Rift neighborship between them. And the same happens on the green level by the reflection on the blue level. Okay, and this is very important because if I lose a link and I have suboptimal routing, the guy at my level knows that I lost the neighborship towards a certain prefix, and he can start advertising the more specific prefixes that I've lost the connectivity to, okay, along with the default. In this case, the below layer will be able to route towards the surviving node or the best node, and the optimal routing or black hole. Optimal routing is achieved and black hole is avoided. This is a very important. So, in order to, there are some other concepts here. Basically, Rift has a full neighborship management state machine. And Rift is using LIE, L-I-E, which is a local information element. You can think about that as hellos, basically. And but these hellos are very different from OSPF or ISIS hellos because they contain different informations. One important information that they contain is the level. Okay, if you take a look at the right side of the slide, you can see that I will provision each box with the level. By default, the boxes are starting with level 0 because in modern data centers, adding a leaf is something that happens more frequently than adding an aggregation or spine device. And so this is something that helps to achieve zero-touch provisioning, okay, which is not yet there, but in the next version of the draft will be there. Then, by exchanging this LO, there are some rules that prevent neighborships from forming, and those rules will also make the protocol able to spot miscabling. Indeed, for instance, I check the level. If the level is one level greater than me, then I can establish the neighborship. If it's greater than one, I cannot establish the neighborship, and this is reported like cable misconfiguration. If you take a look at the cable that goes from B0 to C0, the level is higher than 1 because it's a connection between level 2 and level 0, and so the neighborship can be established. Okay? And this was strict in draft version 2. Now it's more relaxed because RIF now supports east-west neighborship, and so if the level difference is 0 or 1, then the neighborship can be achieved. Then there is another concept that is the concept of point of delivery, which is pod. And in RIF terminology, a pod is a portion of the data center that is connected at superspine level. So in this slide, we have pod 1 and pod 2, and not pod 0, and I explain why in a moment. And if A1 try to form a neighborship with the B1, it can't, because they belong to different pods. So another information that is carried in the lies is the pod number. There is a special pod number, which is pod 0, which is, by the way, the default. Pod 0 means any pod. And pod 0 is, of course, needed at the superspine level, because the superspine level must be able to build neighborships with all the aggregation level, with all the spine level, okay? And so they must belong to any pod. And this is the automatic deaggregation, okay? This is not my presentation, guys. You were lucky, because in my presentation I added all the bit in the title, and I don't remember them on memory, so I will not try to do that. But basically, what this picture depicts is exactly one of the most important characteristics of Rift. That is, if we take a look at this topology, okay, we have a prefix 1, which is advertised by the blue box right at the bottom of the, by the rightmost leaf device. And because of how ties are flooded, and because Rift behaves as a link state protocol in the north direction, the P1 will reach also the supercore level, the superspine level. Okay, because in the northbound direction, the prefix tie, which is like an LSA which contains the prefix, are flooded up to the highest topology level. But then, as I said, to the south, only the default route is, let's say, advertised. In this case, if the upper red box loses its link to the green box there, then it will have a big problem in reaching P1 prefix. And so, if we take the role of these two guys here, they will route according to the default route. So they will send the packet to the aggregation boxes here. But half of the packets will be black hole because because the left aggregation box will send ECMP traffic to both cores, but the upper core has no reachability of P1 anymore. So, because the below supercore has received the information about prefixes and neighborship by the green device through the use of the reflection property that I explained before, and this is how the tie flooding works. Okay, the ties are flooded in this way. So P1, the red box below will check the neighborship of the red box above, and it will notice that the red box above has no way to reach P1 anymore. And so it starts to advertise P1 explicitly, automatically, to the green box, and in this way the connectivity is restored, because the green box will use just the below red box to reach P1. This happens because of a very fancy algorithm that I couldn't even understand in the draft, but I have a prototype on my laptop and I can assure that it works. And another very important characteristic of Rift is that it can reduce flooding. And we are testing performances with this prototype, and we see that if we have enabled the flooding capability, the reduced flooding capability, we can achieve 30, 40, almost 50% of better performances. How does it work? Basically, because of the information that are exchanged through the ties, the topology information element, all the boxes on the same level have the visibility of what the other box of the same level are seeing. So they know neighborship, they know prefixes, and so on. If two boxes at the same level have the same set of neighbor, they can start an election process that is very similar to what happens in EVPN when you want to load balance. Okay, and this election process is done using hashing function. Okay, and so I can elect a flood leader, which is the terminology in the draft, a flood leader, and the backup flood leader that will take care of tie by tie flooding. Okay, so I mean, just to simplify, if I have 100 ties to flood, okay, if you take a look at B1 and B2, they have the set of neighbors. They can see C1, C2, C3. They can see A1, A2, A3, okay? And so they can elect a flood leader. They can form, let's say, a flood set, okay? And they can elect a flood leader. And the flood leader is elected on a tie-by-tie granularity. So it means that if the hash function works well, 50 of these ties will be flooded by B1, and 50 of these ties will be flooded by B2. Okay, and this reduces a lot the information that are spread to the network, and improve a lot the I/O on the control plane. And this brings very good performance improvements especially when you have a large number of ties to flood. Other interesting characteristic is that Rift supports policies. And it supports policies in both directions. Not only in south direction because it's a distance vector, but it supports policies in upper direction as well. And with those policies, it's possible by using communities. Today, the draft defines some communities in order to achieve some use cases. But of course, we can expand a lot the use cases. And with policies, we can do traffic engineering because we can accept and we can install next stops based on policies. So I can choose a path based on policies, very similar to what's achievable with BGP. Another interesting point is that all the packets are modeled using Thrift. I didn't know what Thrift was, okay? But now I pretend I know. But basically, Thrift is like, I don't know, preprocessor or serialization. I don't know, preprocessor basically. You can model the packets. You can define that the ID, the Rift ID must be 64-bit long, or that the IPv4 is 32-bit long, and so on. And then Thrift will be able to interface with every kind of code you can write. So you can write it with Ruby, with Python, with C++, with C, whatever. And if you need to change the protocol format, you have just to change the Thrift model. So it's very, very easy. In fact, one of the, let's say, one of the conditions that must be met in order to be a neighbor is that both neighbors must share the same Thrift major version, because it's so easy to change protocol definition that the standard mandates that if you change some specific things, you must change the major version of the protocol. Because if you change some things, then you make the new protocol not interoperable or not fully interoperable with the new one. So by changing the major version, you will prevent neighborship from forming, and you will prevent unexpected behaviors, let's say. If you change only some, let's say, other definition, less important, then you must change the minor version, but the minor version will not prevent you from forming neighborship. It's channel agnostic. I mean that from a pure transport standpoint, you can use whatever you want. We have evaluated to go with multicast MAC, like ISIS, or with protocol number like OSPF, but at the end, we ended up that it was better to go with the transport protocol and then carry Rift as a payload of this transport protocol. The current implementations that are being written these days are based on UDP, but another interesting point is to use QUIC. Is another point and is another good protocol, transport protocol, which let's say that the first tests are not good enough. So today, UDP is the best preference. Then we can choose how much information we want to pack in each tie. For instance, I can originate a prefix tie for each prefix, or I can pack more prefix in a single tie. This is just an implementation step. There is no purging. So basically, the information never age out. They will age out only when, for instance, a node restart, then a new neighborship is built, and then by using sequence number, the new node will automatically purge the stale information. There is a quite interesting algorithm to do that, but go to the draft. Maybe you can understand it. I can't. And then I can use, as I said, key-value as an opaque information transport to transport basically whatever I want. Because as it's key-value, I need only to define key and value, and I can use it if my implementation can consume them. So, we think that with Rift, you have a lot of advantages. Some are inherited because Rift is a dual source protocol. It behaves like link state in north and like distance vector in south. So it can get both advantages from both worlds. So Rift implements the fastest possible convergence. Rift embeds BFD. So to handle connection fault awareness, automatically you can start BFD using the ID that is carried into the LI. You remember the LI, the yellow? The yellow contains a 32-bit, I think, a 32-bit number, which is the ID. And this ID will be used as a discriminator ID for BFD. So it's completely automatically auto-configurable. There is an automatic detection of topology because north information are carried everywhere. So all the routers have basically the view of the whole topology. There are minimal routes on Tor because indeed, if everything is working, Tor will see just the for route. And this is it. And of course, the prefixes that are local to the Tor, of course. The ECMP is automatically solved. I mean, it's automatically handled. Rift achieve the blast radius of 1, which is the best blast radius in case of fault. Only the nearest devices are impacted. Okay? If you are two hop away of the failure, you are not impacted at all. It's very easy to decommission the nodes. Okay, you can take it and substitute. Okay, of course, yes. And it's up to you how to handle the propagation update performance. You can pack a lot of information in one single tie, or you can use a tie for prefix. It depends also on the applications. If you have a very dynamic application, VMs, let's say, because we would like to port Rift also on bare metal servers, then it makes sense to have a tie for each prefix because you react faster. If you have very static applications, you can have one tie that carry a lot of prefixes. It's just up to the implementation. We also fixed some disadvantage of link state or distance vector. For instance, we optimized the flooding with the hashing feature. And also we have the automatic neighbor detection and the miscabling feature that are not addressed by automatic neighbor detection is not addressed by BGP. Cabling misconfiguration is not addressed by neither. And we have the automatic disaggregation of failure, as I said. You remember the reflection and the fact that I can start advertising more specific prefixes in order to restore connectivity or to achieve optimal routing. And we can use a key value store in order to transmit opaque, whichever you want, opaque information. We have an early implementation because we are not alone in the draft, but we are with a couple of big service providers that are very, very interested in this protocol. I'm done, I think. And we are using a lot of new stuff. So the development of this protocol is very, very different from what we are familiar with for other protocols, like BGP or ASIS or whatever. We are using Redis to stream information. We are using Thrift to model the packet. We are using a completely asynchronous and multi-threaded implementation to take advantage of all the multi-core CPUs that are very familiar, very common today. It's very easy to port it across every platform. You can have it running on, I have running it on Linux and Mac OS, for instance. I have this prototype running on Linux and on Mac OS. Of course, it will be running on Junos in the near future, and we hope that it will be running on all vendor devices, because we believe it's a great protocol to deploy in spine and leaf topologies. Those are some topologies that the creator of Rift is using to test the binary code that I mentioned. So we have 3 pods. Each pod has 4 aggregation switches, and then each aggregation, and the leaf level, we have 2 leaves on each. And each of the leaf are advertising 100 prefixes for this particular, let's say, lab. And those are simply some, let's say, baseline numbers that we collected on Mac Pro, which was powered like that. i7 with 4 real cores. If you take a look at no, I don't know. Okay, if you take a look at the amount of flooding, because it's one of the figures that impressed me a lot when I saw this kind of it is very, very powerful. In this case, we have no fluid reduction applied here, so it's not very. But if you applied it, I tested myself. I can assure that you can save 40–45% of time in terms of flooding and calculation. Okay. I think that I'm pretty done. If you want, if there are questions, you can make questions. I can't assure you that I will be able to reply, though. So if you want to make a question, you are very welcome. In case I cannot reply, I can take it to Anthony, who is the Rift daddy, and get back to you in case. So any question, guys?
Thanks very much.
I said no questions.
Just a quick question. I don't know if you'll be able to answer or not, but when you were saying that, sorry, Brian, I'm Brian from TWT. I'm the one who asks questions today. But talking about the major releases that aren't compatible with each other, how would you upgrade a platform without causing downtimes or loops or whatever? Because if you start from your different layers, you're going to have to, start, and you're going to be building a new one that's not going to talk to the old one.
Yeah, it depends. If you have made small changes and then you are changing just the minor version, then no problem. If you are upgrading the major version, we are in version 3 today, I think. So if the draft change again and we will implement version 4, then you have to plan carefully the migration, because as I said, if you upgrade the switch from version 3 to version 4, then you cannot form neighborship and the switch is isolated. What you can do is you need to leverage the topology, and so to carefully plan the migration. This is the only thing that I can think of, because otherwise
you're going to need to have a time when there's a switch from one to the other, and okay.
Yeah.
A maintenance window. You need a maintenance window.
Yeah, very big, not a window. But I think, according to what Anthony thinks, I've talked about this protocol yesterday with him, and he thinks that he will be able to fix all the big information and, when the RFC will be published. This is the goal, in order to be able to change only what will not cause this kind of burden. This is the goal. Of course, nobody has the crystal ball, and so we don't know if in the future we will have different use cases that will not be able to be handled with the version, the final version of Rift. Let's say that we are trying to open the protocol also to other topologies, exactly to avoid that. For instance, I said that until draft 02, so Rift version 2, no east-west links were handled, okay? But in the real world, we find that sometimes, or very often, or more often than we expected, there are east-west links. And so in the third version of the draft, the possibility to add in the east-west links is addressed. Another thing that will be addressed before releasing the RFC is zero-touch provisioning, auto-configuration. You remember that I said the node will start with level 0, pod 0, and so on. This is not enough, because I can auto-configure the leaf, but I still need to configure something at the other level. At least I need the level, at least. I can leave pod 0, okay, but I need at least the level. Of course, this protocol is built over, to be run over unnumbered links, so you don't need to number everything. It's just link local connectivity with IP enabled. So you need a fake IP address. I mean, an unnumbered loopback is more than enough to allow the protocol to do its magic. And so this zero-touch provision, auto-configuration, was not inserted because it can't prevent miscabling. Because if I want to zero-touch, I must be careful where I connect the devices, because I must assume that if I connect the device, this connection will be okay. So it's another point that in the draft number 4 will not be addressed. I mean, how to have miscabling at zero-touch provisioning to leave at the same time on the implementation. This will not be covered. Okay. Have a good lunch, guys. Thank you very much. You had to deserve the lunch, so.
Thanks very much. Sorry for cutting out, but yeah, we can take it offline. And thanks very much, Massimo.